Yes, good morning. Uh, do you have any questions you want to ask before we start? Anything on your mind? Nothing? Okay. We're only left with a few sections. Today, the first thing I want to do is finish this chapter 11 by looking at motion in space. It's really very simple. What happens in motions in space? It's just the idea of position, velocity, and acceleration. These things, if you've done physics, you know what they are. So we'll just remind you a little bit about these things. So you imagine something moving either in 2 dimensions or 3 dimensions, doesn't matter, in the space or in the plane. Yeah, particle moving like this. Could be a plane, it could be anything, an electron, whatever. And at every time t, at each time, you can know the position of this particle by giving the vector, this vector, which is the vector position rt. So this is the position vector. Of this object, which is moving, yeah, at every time t, you have a certain position, which you can describe by a vector position like this. So r is the vector position, so it gives you the position of this particle in the plane or in space. Then if you differentiate the vector position, what do you get? The velocity, yeah? I'm sure you have done all of this in physics. So if you differentiate the position, you will get the velocity of this particle, and which is also a vector. And in fact, it's a vector. We may have mentioned this before. The vector velocity is tangent to the curve. So this will be r dash, which will be the velocity. So from r, we can get the velocity. From the position, you get the velocity by differentiating. And if I differentiate the velocity, we get the acceleration. That's it. So basically, then r double dash is, we usually use a, and this is the acceleration of this object, whatever it is, the acceleration. Now, so there are 3 things here: the position, yeah, which is the vector r, the velocity, which is the derivative of r, and the acceleration, which is the second derivative of r. Okay? Now, what is the speed? Do you know what the speed is? Sorry? Yes, exactly. From the velocity, if we take the magnitude of this velocity, its magnitude, remember we used 2 lines like this, then this will give you the speed of this object, whatever it may be. That's it. So that's basically what this section is about. But of course, in the questions, it can go all sorts of ways. I could give you the acceleration, yeah, and say find the velocity. How do you do that? You integrate. You integrate the velocity to get the position vector, etc. So you can go in different directions in these questions. So yeah, so the first page is just a bit about what we just said. So this is the position vector r. The r dash is the velocity. The magnitude of r dash is the speed. And of course, if you want the length of the curve from, we've already seen this before, S of t. If you want to find the length, then you just integrate the three components, f dash, g dash, h dash squared. Okay, here is first example, very simple. Find the velocity and acceleration vectors if the position is given by r of t. Now, in this question, are we in 3 dimensions or 2 dimensions? 2, yeah? You can see the position vector only has 2 components. So then you will say the velocity v of t, yeah? It's a vector, so I can put an arrow. It's the derivative, yeah? It's r dash. And last section, we knew how to do this. So what will be the velocity? 3t squared, the first component, and the second component is 4t. That's it. So that is the velocity. Of course, I can get this velocity at any time I want. For example, the initial velocity, if you want the initial velocity of this particle or object, what will it be? 0, 0. So it's basically the vector 0, yeah? If you want the velocity 1 second later, say, yeah, at t equal 1, you will get the vector 3, 4, etc. So that's the velocity. And then we want the acceleration, 2, acceleration, a of t, yeah, acceleration. Is, of course, the second derivative, yeah, r double dash. So it's the derivative of the velocity also. So it's going to give us 6t, yeah, and 4, like this. All right. And then again, you can find the acceleration at any time you want. For example, the initial acceleration is 0, 4. This acceleration will never be 0. Can you see why it's never going to be 0? Because the second component is always 4. So it will never be equal to 0, basically. So that's the general idea. Okay, 1 second later, the acceleration becomes 6, 4, and so on. Okay, so very simple. No issues at all. Here, we are doing something a little bit different here. What are we given here? We are given the acceleration, exactly. And we want to find the velocity and the position. And to do that, we need a bit more information. We are given that the velocity at 0 is this vector 2, 0, 1, and the initial position is this vector. So using all of this information, I want to find the velocity and the position. Okay, first the velocity. I will find it by integrating the acceleration. So integrate the acceleration. Okay, so we will integrate 6t. So what do we get if we integrate the 6t? 3t squared plus a constant, huh? Don't forget the constants. And then 12t plus 2, 6t squared plus another constant. And number 3, yeah, e to the power of t. Yeah, it's e to the power of t plus a constant, a third constant. Now, this is not the end of the story. I need to find C1, C2, and C3. How? By using V of 0. So V of 0, let me substitute. So that means T is 0, yeah? So it's going to give us C1, C2, and not C3. What is not C3? Huh? 1 plus C3, yes. Because e to the power of 0 is what? 1. Can I have your attention, girls? I think. Can you focus on this? Okay. And we are told that this v of 0 is what? Is which vector? 2, 0, 1. So that means, so C1 is 2. First result. Second, yeah, this C2 is 0. C2 is 0. And finally, the third one, 1 plus C3 is equal to 1. Yeah? Or no? So C3 is 0. So now from here, C3 is equal to 0. Okay. So finally then, therefore, our velocity will be 3t squared. I go back here, yeah? Then 6t squared plus 2t. And then, sorry, C1 is 2, huh? So, plus 2 here, yes, sorry. Plus 2, of course. Yeah. So it's going to be 3t squared plus 2, 6t squared plus 2t, and then e to the power of t. And that is our velocity at any time t. Okay. So that's the velocity. Second thing we want to find is the position. Velocity, position. Now, number 2, the position, which is the vector r, yeah? And you find r by integrating the velocity, v. So it's going to give us the vector t to the power of 3 plus 2t plus a constant c1, then 2t to the power of 3, so plus t squared plus a constant c2, and then e to the power of t plus a constant c3, like this. Again, that's not the end. We need to find what? What do we need to find? the constants, yeah? C1, C2, and C3. We need to find them by using this information. R of 0 is 0, 3, 5. Okay, now R, yeah, R of 0. So first I substitute, so it's C1, C2, and 1 plus C3. And this is equal to 0, 3, 5. Okay, 0, 3, 5. That means C1 is 0, C2 is the 3, and then 1 plus C3 equal to 5, which means C3 is 4, like this. And therefore R of t will be the vector, this, and then 2t3 plus t squared plus 3, and then e t, and that is our final answer in this question. 4, huh? Plus 4, sorry. Yes, I need to add this. Plus 4. Are we okay with this? Yeah? All right. So that's basically R of t, and that's it. Basically, that is the section. Maybe we just have just a couple of questions here, maybe. Okay, find the velocity and acceleration if r is equal to this. Okay, so the velocity, what is the derivative of 5 cosine 2t? Yeah, the 2, remember, comes up, so it will become 10, but the derivative of cosine is minus sine. So in the end, it will be minus 10 sine 2t. And the same thing, the 2 comes out. 10, the derivative of sine is cosine, like this. So that is the velocity. The acceleration will be minus 20 cosine 2t and minus 20 sine 2t, like this. Okay, that's fairly easy. No major issues here. And the 3 is simple. You can differentiate this. So it's a question of differentiating the functions. Here, you need to differentiate, but if you want to differentiate this one, for example, what do you need to use? You want the derivative of this function? The product rule. Yes, you need to use the product rule. For this one, you need to use, it's t over t squared plus 1, the quotient rule. Yes. So here, it's uv. Here, it's u over v. So you can differentiate this without. And the middle one is like the power rule. It's power half. It's t squared plus 1 to the power of half. So you bring half down, etc. So you need to check the different rules. Okay. here in these questions, it's a matter of integrating. Yeah. So 1, 2, 1, 3, 5 is a differentiation problem. You need to find derivatives. Here, we are given the velocity. We want the position. So it's a matter of integrating this function. So let's try it. R of t. So R of t will be the integral of V of t okay. The integral of 10t, yeah, plus a constant, and then minus 32t plus 4 will be minus 16 t squared, yeah, plus 4t plus a constant c2, like this. And then we are going to use this condition to get the constant c1 and c2. So you say r of 0. First, substitute t with 0, so it's going to give you c1, c2, so? And this is equal to 3, 8. That means c1 is the 3, and c2 is 8. And that's it. After that, you substitute. So the position vector is 10t plus 3, and then minus 16t squared plus 40 plus 8, and that is the position vector for this question. Okay. Let me do the last one, 13. And then, yeah. So try the others. Obviously, you can check them. I just want to do this one. Here, we are given the acceleration. So what do we want to find here? Velocity and the position vector r. The velocity v and the position vector r. So v, first we are going to find the velocity by integrating the acceleration. So it's going to be half of t squared. Yes? Plus a constant, yeah, plus c1. And then the integral of 0, not 0, c, yeah, it's a constant. And then minus 16 plus c3. Now we're going to get c1, c2, and c3 from v0. Yes. Now v at time t equals 0 is, first of all, by substituting t equals 0, it's c1, c2, c3, and then by using the information, it's 12 minus 4, 0. That means c1 is 12, c2 is minus 4, and c3 is 0. Yes or no? Yes. Yes? So can we write the velocity now? Yes. We can, yeah? So the velocity at any time t is going to be half of t squared plus 12. And then negative 4 or minus 4 and minus 16 t, and that's the velocity. And then we do the same now to find the position vector. So we are going to now move into R by integrating the velocity. So you can see really it's important, you know how to integrate, differentiate, and so on. That is really the basis of all this work in calculus 2. Now, we integrate half of t squared, so it's going to be 1 over 6 t to the power of 3, so, yeah, plus 12t plus constant c1, and then minus 4t plus c2, and then minus 8t squared plus c3. Okay, and then we're going to use r of 0. By the way, it's not always 0, yeah, they can give you different, here they're doing it with 0 all the time, but it could be t equal 1 or, so r of 0, so we substitute basically t equals 0 in this equation. So it's going to be C1, C2, and C3, yes? And this is equal to 5, 0, 2. So that means C1 is 5, C2 is 0, and C3 is 2. Therefore, the position vector R of t is going to be 1 over 6 t to the power of 3 plus 12t plus 5, and then minus 4t, and that's it, and then minus 8t squared plus 2, and that is the end of this. Any questions regarding this? It's very easy. Yeah, they're really simple. There's no major issues here at all. So that is this section 11.3. So I'll just take a few minutes. I want to close this down and then get to the next section. Okay. Okay, so we'll come back. Now we have this section, 14.1. We're basically left with three sections, 14.1, 14.2, and 14.5. So today I'll take a look at this 14.1. Next week I will spend the whole of Tuesday solving with you some questions regarding the test so we can review properly, make sure you are ready for the test on Thursday. So that's why I want to do these sections, put them aside, then we can focus on the test and reviewing a little bit next week. So you are okay for the test number 3. All right, so vector fields are basically functions. A vector field is a function f of xy, which basically gives you a vector. It takes a point xy, f of xy is a vector with two components, f1 and f2. In 3 dimensions, f of xyz is a vector, but of course with 3 components, f1, f2, and f3. So vector field basically is a function whose value is a vector, either in the plane or in space. So here is an example of a vector field. And I want to evaluate f at the point 1, 0. So what do we do? What is x here? If you want to find f at 1, 0, so x is 1, y is 0. So you substitute in the function and you will get a vector. What will be the vector? 1 plus 0, which is 1. 3 times 0 minus 1, so minus 1. Yeah, like this. And if I want to plot this, so let me look at it in an xy plane, x, y. The point 1, 0 is here. Yeah, that's the point 1, 0. So at that point, what is the value of the function? Minus 1. 1 minus 1, yeah? So 1 along the x-axis and minus 1 along the y-axis. So it's a vector which is like this. This pen is not working properly. So I have a vector, yeah. Like this. F at the point 1, 0 is the vector 1 minus 1, which is here. Now, I also want f of 0, 1. What is the vector f of 0, 1? 1, 3. Yeah? So if I go to the point 0, 1, which is here, at that point, the value of the function is a vector 1, 3. That means 1 along the x-axis. How many along the y-axis? 3. So you will get a vector which is a bit like this. Yeah. So this vector is the vector f of 0, 1. And at the point minus 2, 1, if you substitute into the function, so yeah, minus 2, 1. So it's going to be minus 1, yeah. and yeah, 3 times 1, 5, yes, 5. So it's minus 1 along the, so let me go to the point minus 2, 1, which is here. So at that point, yeah, minus 2, 1. At that point, the value of our function is the vector minus 1, 5. So minus 1 along the x-axis, and how many along the x-axis? 5. So it's going to be a vector like this. Minus 1 along the x-axis, and 5 up along the y-axis. So this vector you see here in red is the value of the function at minus 2, 1, like this. So in the end, if you draw all these vectors, you will get like a field. You know what a field is? Yeah, a field of vectors. Many, many vectors. So you get, that's why it's called basically a vector field. So at each point you have a vector. And yeah, you get something a bit like this, what you see here in this graph. All right. Now, we talk about for any scalar function f, the vector field given by the gradient of f is called the gradient field for the function f. Okay. So the gradient field, so you have a function here, for example, f of xy, which is x squared y minus ey. The gradient of the function f, we have seen this function before, yes? What is it? It's the vector df over dx at xy, the first component. The second component is df over dy. Yeah? Do you remember this gradient function? Yeah? This is called the gradient field, or just the gradient function. Yeah, the gradient field. So, yeah. So what will it be here? What will be the gradient of this function f? So it's going to give us 2xy for the first component. What will be the second component? df over dy will be x squared minus the derivative of e to the power of y, which is ey also, like this. So that is the gradient of this function f here. So f, its gradient. Again, this of course is a vector field. At, for example, if you want the gradient at the point 1, 1 or 1, 0, say, what vector will you get? If you want this gradient at the point 1, 0, what will it be? 0? 0, 0, exactly. If we want it at, let's say, 2, 0, it's going to be 0. Yeah, 4 minus 1, which is 3, etc. So at every point xy, you're getting a vector, which is basically the gradient of the function f, which is given here. Now, so every function fxy has a gradient like this. which is a vector field. Now, the question sometimes we have is that we have, what happens if we have a vector field F, so you have a vector field, it's given to you, F of xy, yeah? Let me write it. Can we find a function small f such that the gradient of f is exactly equal to this function f of xy? So the vector is given. We want to find a small function, a function small f, such that the gradient of this f is exactly equal to this one. So this small f is what we call the potential. F is called, yeah, the potential function. Of this function f that we have. Right, now this question is a little bit more difficult if you want. So I want to solve. Let me just explain what we want here. So suppose I give you this function, f of xy, just, this is a vector field, yeah? This is a vector field. For example, f of 1, 0, of course, will be just the vector 1, 0, etc. So you have this, this vector field. The question is, find a function f of xy such that the gradient of f is exactly equal to this f that we are given. So, can I find such a function, small f, like this? So, what I want then is a function small f so that the gradient, what is the gradient? The gradient is df over dx, df over dy. I want this to be equal to x, y. This function is xy. This gradient is df over dx and df over dy. So that means df over dx should be x. Yes. And df over dy should be y. Can I find the function f like this? Okay, let me show you how we will find this function small f. This is a really a classical question in calculus. You have a vector field, you want to find its potential. So you have a vector, you want to find a function whose gradient is exactly equal to that vector. Okay, the way we do that is not very difficult, but it requires. So let me call these equations 1 and 2. So what I will do is I will integrate the equation 1 with respect to x. So I will integrate. If you integrate df over dx with respect to x, you will get the function f. because when you integrate the derivative, you go back to the function. And when you integrate x, what do you get? No, integrate. X squared over 2 plus a constant. Constant with respect to x, but it could be a function of y. So I will call it g of y, just the function of y. Then, okay, after you do that, now let's call this equation 3. I will differentiate 3 with respect to y. So this left side will give us df over dy. The right side, this half of x squared, when you differ 0. And then you will get g dash with respect to y. And according to equation 2, this df over dy should be equal to y. Yes. Now, if g dash is y, so what is g then? G dash, the derivative of g with respect to y is y. It will be y squared over 2, yes. Plus a constant. Now, once we have this, we take it here, and we have our function f. So, f of xy, which we are looking for, is half of x squared plus half of y squared plus constant c. That's it. Now, let me check. What is the gradient of this function f? Its derivative with respect to x is x. What is its derivative with respect to y? Y, finished. So yes, the gradient of this function is equal to xy. So find the function so that the gradient is xy. Well, we found it. It's half of x squared plus half of y squared plus a constant c. So the question here we are solving is, I give you a vector field given. What are we looking for? Find the potential, which is a function f of xy, which is called the potential. Such that the gradient of this function is exactly the vector field we are given to you. This question really important in mathematics. If you do further maths, you will find this question many times in different situations. Okay, let me do one other example, and that's basically what this is the important part of this section. There is nothing else here. So let me go back and see. Okay. All right, here. Here is a vector field. I want to find its potential function. If it exists, sometimes it will not exist. If it exists, we will say that f is conservative. Conservative means it has a potential. Okay? If the potential does not exist, by solving, we will find some problems somewhere in the thing. Okay, so let's do A, and you will be fine after. So here is our vector field. F of xy is the vector 2xy minus 3 x squared plus cosine y. So what I want is to find a function f of xy such that the gradient of f is this function that they gave us, the vector field. So I want, you always start like this. So you want the function such that its gradient, meaning df over dx, df over dy, should be equal to 2xy minus 3 and x squared plus cosine. Now you split this into two equations. The first one is df over dx should be equal to 2xy minus 3. And the other one is df over dy should be, very good. Now, do you remember what we did after this? We integrate 1 with respect to x. Yes. So integrate one with respect to the variable x. It's always like this. It's a nice method. It's not very difficult, really. So just follow it, and you will, and things should work out. So what you get on the left is always the function f, because you're integrating its derivative. So you're going back to the function. What you have on the right, of course, depends on here. What will it be? Very good. Minus 3x plus a function of y. Yes, plus a function of y. It's a constant with respect to x, but it could be a function of y. So we call it g of y, or you can call it any other thing. After this, what do? We differentiate this number 3, differentiate 3 with respect to y. So you will get df over dy on the left side. On the right side, x squared plus the derivative. When I put g dash, of course, it's the derivative with respect to y. And we know that according to 2, this should be, according to equation 2, df over dy should be x squared plus cosine y. Now here, what happens? If the potential exists, the x's will always cancel. So what are we getting? G dash is equal to cosine y, which means that G is sine y, yes, plus this time a constant, like this. Now what do we do with this? We take it back into the function. So our function, our potential, yeah, is x squared y minus 3x plus, that's it. Now, if you want to check that this work is correct, what can you do? Find the gradient. This gradient should be exactly equal to the function we started with, the function f the vector field, basically. So if you want the gradient of this function, just as a checking, the gradient, the derivative with respect to x will be 2xy minus 3. And the derivative with respect to y is x squared plus cosine y. And you can check, you can go back to f and see that it's exactly the function, the vector field we started with. So yes, it's okay. We have found the potential of the vector field we started with. Does that make sense? Yes? It's kind of a long process. B, we can check B if perhaps, yes. Okay, let's try B. We don't know if it's conservative or not, but we will see what happens. So let me solve part B. If it's not conservative, then something will happen. So here it's 3x squared y squared minus 2y, and then x squared y minus 2x, like this. df, so if there is a potential, df over dx should be 3x squared minus 2y, and df over dy should be minus 2. So we are looking for a function small f which will have these two properties. So now, as usual, we will integrate integrate. By the way, I could integrate 2 here, it's okay. Integrate 1, I could start with 2 if I want, with respect to x. But if you integrate 2, then it will be with respect to y, yes. So if you integrate 1 with respect to x, it will give you f of xy equal to x cubed y squared, minus 2yx plus a function of y. And then differentiate this one, differentiate 3 with respect to y. Okay, now we want, so df over dy with respect to y, so 2x cubed y minus plus the derivative of the function g, and this, according to 2, should be equal to x squared y minus 2x. And this, I think we have a problem here. Because if you look at this, this equation, okay, the minus 2x will go. So what we're getting is 2x cubed y plus g dash of y equal to x squared y. So that means g dash is
x squared y minus 2.
No. Is this possible? Can you have a function of y and then on this side you have x and y? Not possible. Can you see the problem here? So what does this mean?
Not conservative.
It's not conservative. There is no potential. This function f, capital F, g rather. I think I used, this function g, vector function here, has no potential. Yeah. So here, because there is x and y, so g is not a function, g dash is not a function of y only. It's not a function of y only. So g is not conservative. That means it has no potential. There is no potential. Like this. Are we okay with that? Yeah? So that's all there is in this section. Again, maybe just okay. Can I ask you to write your names, please? Okay, here find the gradient of these functions. So the gradient of f will be uh, 2x, 2y. That's it, yeah. 2x, 2y, the gradient, no problem. How about this one? What will be the gradient of this function? (23). If you want the gradient of this function, so yeah, we need to use the product rule here. You need to use the product rule, u and v. So the derivative of this function with respect to x, u dash v. So it's going to be plus, I think it's going to be minus. Minus u v dash. What will be v dash? Yeah, minus y. So it's going to be minus xy e minus xy. So that is the derivative with respect to x. And then with respect to y, there is no need to use the product rule. It's just x, which is a constant. And then the derivative of the second one with respect to y, which will give you a minus x, yes? So it's going to give us minus x squared. So, yeah, good. So minus x squared e minus xy. That is basically the gradient of here. Same thing. Let me just do this one. So to differentiate this, it's probably better to think of this as the power half. Yeah. So you want the gradient of this function. Its derivative with respect to x. Yeah. So we need to bring the half. Yeah. Half. Yeah, and then all of this to the power of minus half, and then multiply by the derivative of this, which is 2x. So 2 and 2 will cancel here. So in the end, what you will get is x over square root of x squared plus y squared plus z squared. This is for x. For y, it will be y, and for z, it will be z. So no problem. So this will give you the gradient. Okay, so when you have f and you want its gradient, it's very easy. It's no problem. It's just a matter of finding the partial derivatives of the function. It's not a problem. It's the other way that is a little bit more difficult. Here, you have the vector field. Determine whether or not the vector field is conservative. If it is, find a potential function. Okay, so here we have our vector field. What we want is find the potential. That means the gradient of f should be equal to the vector field. So in this case then, we will have df over dx equal to y, exactly. And df over dy should be x. Now, integrate this one with respect to x. F of xy should be? No. We integrate, yes? Yx, yes. Xy. Plus a function of y. Yes. And then differentiate this with respect to y. So df over dy is x plus g dash, yes? And this should be, according to this equation 2, it should be equal to x, yeah? Does that make sense? So we go from 1, integrate, differentiate with respect to y, and then use the second equation 2 to get something like this. Now, this is telling us that g dash is 0, which means the g is c, yes, a constant. And once you have the g, take it back into the function f, and you are okay. So that means now our function f is xy plus a constant. Again, you can check if you want that the gradient of this function f is yx. What is its derivative with respect to x? Y. Yeah, you can see it here. What is its derivative with respect to y? X, and it's exactly here. So, like this. Okay. All right, let's do one last one, girls, 33, and then we can stop. Can you try it? Can I give you a few minutes to try this one? Try it, please. Try it. You can work together. You can, yeah. So you want to find a potential for this vector field. So this is our function f. I don't know if it exists, by the way, or not. Yeah, we will find out. So the question is to find f such that the gradient of f is equal to. So try it. If you understood what we did, you should be able to do this without too many problems. You found it? Is it conservative? Yes. Check, but just double checking. Anyone else? What's the answer? Are you done? You found the f? Okay, good. Okay then. All right. Let's do it together. If you haven't done it, it's fine. So what we are looking for is a function f such that its gradient is equal to this vector field. So you want the function such that df over dx should be equal to x minus 2xy. Okay, good. And you also want 2f over dy to be y squared minus x squared. So that's really what you want to have. You want to have a function for which satisfies these two conditions. So like we did before, we will integrate one, yeah, with respect to x, then this will give us f of xy. That's the integral of the left side. Yeah, this integral, if you put an integral sign with respect to x, it's f. Now the integral of x is half of x squared, or x squared over 2, and then 2xy is x squared y, huh? Plus a function of y, which we can write as g of y. After this, we differentiate the 3 with respect to y. So we will get df over dy. This is the derivative of the left side. The right side, when you differentiate with respect to y, you will get, this is 0, you will get minus x squared plus the derivative of g, so it's g dash with respect to y. And this, according to equation 2, this df over dy should be equal to y squared minus x squared. And then you look at this equation to find the g. Yeah? So from here, you can see the x squared and the x squared will go. And we have a function only of y. That means, yes, there is a potential. This function is conservative. G dash is y squared. So that means G is, yeah, y cubed over 3, or 1 over 3 y cubed plus a constant c. And we take this now and put it in 3. Substitute. Now, final step, substitute in equation 3, and you will find your potential as the function. So if we go to 3, yeah, half of x squared minus x squared y plus 1 over 3 y cubed plus a constant. Nice and easy. And you can check, if you want to check this, that the gradient of f, derivative with respect to x will be x minus 2xy. Derivative with respect to y, minus x squared plus y squared, which is exactly equal to the function f, which we were given at the beginning. Yeah? that's it. So, good. So that is then the way we solve this 33. Okay, that's it. We will stop here today. Thank you for your attention, guys. Any questions? Anything? You're okay?